So what's the deal with reality? Where did all of this come from? For ages, those were questions you'd ask a philosopher. But in his incredible book, A Brief History of Time, Stephen Hawking showed us that, nope, these are questions for science. In this explainer, we're going to follow the clues he laid out and try to build a picture of the universe we're all living in.
There's this famous story about a scientist giving a lecture on astronomy. Afterwards, a person comes up and tells him he's got it all wrong, that the world is actually a plate on the back of a giant tortoise. The scientist, kind of amused, asks, "Well, what's the tortoise standing on?" And the reply is, "You're very clever, young man, but it's turtles all the way down." Now, as wild as that sounds, it actually points to something really human. We crave a complete picture of the universe, a theory that explains everything, even if that theory is a giant stack of turtles.
These are the big ones, right? The questions that keep us up at night. So for the next few minutes, let's treat this like a great cosmic detective story. We're going to follow a trail of clues that scientists have been uncovering for centuries to try and crack the ultimate case. Why is there a universe here for us to even see?
Okay, every good detective story has to start somewhere, with that first piece of evidence. For us, that means we got to go way back and look at our earliest ideas about the cosmos, the ones that just seemed like common sense, and see how they got completely turned upside down.
So our case file opens way back in ancient Greece. As early as 340 BC, Aristotle had already figured out the Earth was a sphere just by watching its shadow on the moon during an eclipse. Smart guy. This led to Ptolemy's model, with the Earth right at the center of everything, which, believe it or not, was the leading theory for over 1,000 years. Then, in 1514, Copernicus comes along with this totally radical idea. What if the sun is at the center? But it's just an idea, right? It took almost another 100 years for the proof to show up. In 1609, Galileo points his new telescope at Jupiter and sees moons orbiting Jupiter, not Earth. And that was it. That was the concrete evidence that shattered the old way of thinking.
So, the case was now officially wide open. And then, our first master detective enters the scene, Sir Isaac Newton. And he didn't just find another clue, he basically uncovered the rulebook for the entire cosmos.
This was the absolute game changer. Newton's law of universal gravitation. It basically says that every single object in the universe pulls on every other object. With one single, beautiful equation, he connected the heavens and the earth. The same force that makes an apple drop from a tree is the exact same force that keeps the moon circling our planet. All of a sudden, the universe wasn't some big divine mystery anymore. It was this grand, predictable machine, a kind of clockwork universe that ran on laws we could actually figure out.
But here's the plot twist. Even Newton himself spotted a massive hole in his own theory. Think about it. If gravity is always pulling everything together, then in a universe that's just sitting there, shouldn't all the stars have crashed into one giant cosmic pileup by now? Newton's perfect clockwork universe was actually incredibly unstable. The case, it turns out, was far from closed.
So for 200 years, that puzzle just sat there. And then, at the dawn of the 20th century, our next great detective shows up, Albert Einstein. And he didn't just find a new clue. He completely redrew the map of the crime scene. He realized the problem wasn't the theory of gravity itself, it was our very understanding of space and time.
This was just a monumental shift in thinking. For Newton, gravity was this invisible force, like a rope pulling things across a fixed, empty stage called space. But for Einstein, he said there is no force of gravity. Whoa. Instead, he said that massive things, like the sun, literally bend and warp the very fabric of space and time around them. So planets aren't being pulled by the sun. They're just following the curves that the sun has made in spacetime.
Okay, think of it this way. Imagine an airplane fly in a perfectly straight line over some really hilly countryside. Now look at its shadow on the ground. The shadow isn't going to move in a straight line, right? It's going to follow a curved path going up and down all those hills and valleys. Well, in the same way, planets are just following the straightest possible path they can, physicists call it a geodesic, through a space-time that's been curved and warped by the sun. What we feel as the force of gravity is just what it's like to move along those curves.
So this is our new arena. It's not just space anymore. It's this dynamic, four-dimensional thing called space-time. And it's not some static backdrop for the universe to happen in. It's an active player in the game. It affects everything in the universe, and everything in the universe affects it.
Now, Einstein's theory already suggested the universe should be dynamic, not static. But it was a brand new piece of evidence, a single explosive clue that would change everything and point us directly to a beginning for time itself.
The year is 1929. The astronomer Edwin Hubble is busy mapping out distant galaxies, and he starts to notice something, well, something completely astounding. Almost every single galaxy he looked at was rushing away from us, and fast. The universe wasn't just sitting there, it was expanding.
So how did he figure this out? His key piece of evidence was something called redshift. It works kind of like the sound of a car. You know how as a car drives away from you, the pitch of its engine gets lower? Well, light does something similar. As a galaxy speeds away from us, its light waves get stretched out, and that shifts their color toward the red end of the spectrum. And what Hubble found was a clear pattern. The farther away a galaxy was, the faster it was moving away from us.
This discovery leads to a question that you just can't escape. I mean, if everything is flying apart right now, what happens if you run the movie of the universe backwards? Well, everything must have been closer together in the past, a lot closer.
If you rewind that cosmic clock all the way back, about 13.8 billion years, everything we can see in the universe today, all the stars, all the galaxies, gets squeezed down into a single point. A point so small it has no size, and so dense it's infinite. We call this the Big Bang's singularity. And it's more than just a starting pistol, it's the point where all of our known laws of physics just completely break down. It's the literal edge of our knowledge.
And that brings our whole detective story right up to the present day. We've made some incredible progress, but we've hit a wall. We've arrived at a standoff. See, modern physics now depends on two amazingly successful theories that, well, they completely contradict each other.
On one side, you've got Einstein's general relativity. It's our perfect theory for the really big stuff: planets, stars, galaxies, the smooth fabric of space-time. And on the other side, you have quantum mechanics, our perfect theory for the really tiny stuff, the bizarre, fuzzy world of atoms and particles. Here's the problem. They both work flawlessly in their own domains, but their basic descriptions of the universe are totally incompatible. One says the universe is smooth and predictable. The other says it's jumpy and based on probability. They can't both be the final story.
So any final theory, any theory of everything, has a huge job to do. It has to explain how all four of the basic forces of nature are connected. It needs to unite gravity, the force that shapes the whole cosmos, electromagnetism, which is behind light and chemistry and basically everything you touch, and then the two nuclear forces that hold the very atoms themselves together. The dream is to show that these four things are really just different faces of one single fundamental force.
And this, right here, this is the holy grail of modern physics. To find that one, complete, unified theory, people often call it a quantum theory of gravity, that can describe everything. Everything from the very first instant of the Big Bang to how galaxies formed, how stars lit up, and even how we came to be.
And so our cosmic detective story ends right where it started, with the biggest questions there are. As Hawking himself said, just our desire to understand is reason enough to keep searching. Finding a unified theory probably won't change our day-to-day lives, but man, it would be the ultimate triumph of human reason. And maybe, just maybe, it would finally let us understand why we, and the entire universe, even exist at all.